Hello there, Mr. Sutton here, bringing you the AB Calculus 613 Extra Practice number 3 solutions on volumes with solids of revolution. For this problem, I'm trying to find the volume of the solid obtained by rotating the region bounded by these curves about the line y equals 1. So let me start by graphing these out. So here I am in my y equals. I've got y1 equals the f function, and y2 is going to be the g function. And if I graph these out, let me use a window of, I'm thinking this is going to be pretty close to the origin, so let me go from -2 to +2 and zoom fit that, because I know these intersect at the very least at the origin, and yeah, pretty close to the origin as well for the other intersection point. So there's basically what we're looking at, and the axis of revolution, y equals 1, is this horizontal line up here. So now I have to revolve this region around this horizontal line. Okay, well, I need a few things to do that. For one thing, I'm going to need the limits of integration. So that's just the limits of the bounded region. We know that f of x equals g of x in a couple spots. Certainly right here at the origin, if you plug 0 into both of these, you get the same thing back, namely 0. Also, this looks like it's about x equals 1. I could go on the calculator to verify that, but it's actually faster just to plug 1 in for both functions. F of 1 is 1. G of 1 is the square root of 1, which is also 1. So definitely 1 is also our other intersection point. So now that I've got this, I need to figure out what formula I'm using for the area slices that I'm going to be integrating across this integral. So since I have a gap, a space between the bounded region and this axis of revolution, that means I'm going to have to use washers, pi times big R squared minus little r squared as my setup formula for the area here. So for big R squared, that's the distance from the axis of revolution to the further away boundary of the region. So that's going to be a distance of 1 minus this lower function of f of x, and I'm squaring that. And I'm going to be subtracting little r squared now. So little r, that's the distance from the axis to the closer curve. So that's going to be 1 minus radical x, or 1 minus g of x, whole thing squared. And now let me put this in the calculator. Well, actually, let me get my basic setup first. So at some point, my volume is going to be the integral from 0 to 1 of this a of x dx that I just wrote out here. So now let me do this on the calculator. So I'm going to put the a function in my y equals just to keep things a little more manageable. So I've got a pi, and I'm opening a parentheses now, and another parentheses. In that that next parentheses, that nested parentheses, I've got 1 minus the f function, which is just alpha trace y1, and then I have to square all of that, minus, open another parentheses. Now I've got 1 minus the g function, so alpha trace y2, close the parentheses, square that, close the other parentheses, and now I've got a of x as my y3. Quitting out of there, let me now do the integral, so math 9, from we got 0 to 1, and I'm going to just do alpha trace y3 now, and dx, giving me a grand total of 0.524. On this problem, I'm trying to find the volume of the solid revolution when the area between all these curves is revolved around the x-axis. Let me start by graphing these out. Now, you could do this on your graphing calculator, but you could probably also do it without one. I mean, this is just a line with a y-intercept of 2 and a slope of 1. And then these are the vertical lines at x equals -1 and +2. So here's what the graph looks like, with or without a grapher. And now I'm trying to revolve this around the x-axis. So I already know my limits of integration. We're going to be going from -1 to +2, just because those are our vertical lines. But now how about the area formula that we're integrating across that integral? Well, since my whole bounded region here, this trapezoid here, since that whole area is flush against the axis of revolution, there's no gaps or spaces, that means I'm going to be able to use discs or circles or pancakes as my area. So I've got a of x equals pi r squared. And now the radius, that's just going to be the distance between the outer edge of that region to the axis of revolution. So that's just the function x plus 2 minus, well, 0. So just x plus 2 then. So that's going to be pi times x plus 2 squared. And in general, to get the volume, we're going to have to do the integral now from -1 to 2 of this a of x dx that we just came up with. So let me do that on the calculator. So here's what this looks like on my calculator. Normally I would enter a of x in one of my y equals, but it's such a small expression here that, I might as well just put it directly into my integral. So let me press enter, and that's going to give me 65.973. On this calculator-based free response, we have this shaded region R between y equals x squared and y equals 4, and our first task is to find the area of that region. So we're just going to do an integral from left to right of top minus bottom, basically. So let's find out where these two functions intersect, because those intersection points are the left and the right limits of integration for our integral. So setting x squared equal to 4, well, x is just going to be plus or minus 2 at that point. So I have the integral from -2 to +2 of something. Let's find out what the something is. If we're doing top minus bottom, we're going to have to do 4 minus x squared. So then I have the integral from -2 to 2 of 4 minus x squared dx. And the rest of this I can just do on the calculator, since this is a calculator problem. So here's what I've got on my calculator. Math 9 for integral, -2 to 2, 4 minus x squared dx, comes out to 10.667. For this part of the problem, I want to find the volume of the solid generated by revolving R around the x-axis. So I already have my limits of integration from -2 to 2 of the bounded region, so that's all set. But I need to figure out what kind of area formula I'm now going to integrate from -2 to 2. Since I have space between the bounded region and the axis of revolution, which again was the x-axis, that means I have to use donuts or washers as my area formula. So that's going to be a of x equals pi times big R squared minus little r squared, just a general format for what we're doing. So big R, that's the distance from the further away part of the bounded region to the axis of revolution. So that's 4 minus 0. It gives us that distance. It's just a constant value of 4. So big R is just going to be 4, and we're squaring that inside there. And then we have little r. That's going to be the closer curve distance to the axis of revolution. So that's going to be x squared minus 0, which is just x squared. So in here, then I'm going to have minus x squared squared, because x squared itself is r, and then you're squaring r. So that's a of x. I'm going to put that in my calculator in just a moment. So in general, then, the volume is going to be the integral from -2 to 2 of this a of x, and don't forget the dx. Now let me do that on my calculator. So just to make this a little less unwieldy, I can actually take this pi that's part of the a function here and take it outside the integral. That's just one of my integral rules. So I've got pi times math 9. We have an integral from -2 to +2 of, and now I have all this stuff inside. So that's going to be 4 squared, which I'm not going to bother turning into 16, minus, and now let me put this in a parentheses just to be on the safe side. We have x squared, close the parentheses, and square it again, which I know is x to the 4th, but whatever. And then we have a dx, press enter. All that comes out to 160.850 if I round off to 3 decimals. On this problem, we're told that there exists a number k, which is greater than 4, such that when r is revolved around the line y equals k, so this is a horizontal line that is up here somewhere, the resulting solid has the same volume as the solid in part B. Okay, if they say so, we'll take their word for it, I guess. Right, but do not solve an equation involving an integral expression that can be used to find the value of k. So on this one, we're basically going to set up a problem where we're trying to find the volume that we would get by revolving this around the line y equals k. And we won't be able to because we don't know what k actually is, but we're going to try to do that, and then we're going to set all of whatever we get equal to the volume that we found in part B. So that's our general strategy on here. So in order to start that process and to at least pretend I'm going to try to find the volume, I need to figure out what my limits of integration are going to be. Now, since it's the same bounded region, we're still using -2 and +2. So that's all set. Next, I need to figure out what the area formula is going to be that I'm integrating. So because I have this space here, we've got some kind of gap between the axis of revolution and the bounded region, and we know there's always going to be a gap no matter what k is, because they told us k is greater than 4. So k is never going to be this exact boundary right here. It's always going to be a little bit above. That means we're going to have to use washers. So we have, again, a of x equals pi times big R squared minus little r squared. This time around, big R squared, that's the distance from this further away function to the k line. Well, that's going to be a distance of k minus, this is x squared down here, so k minus x squared. That's big R this time around. And we also have little r squared to deal with. That's going to be k minus this closer boundary of 4. And we're squaring that as well. So all of this here, this is all a of x. Now, when I integrate this for some k value, there's some k value that when I integrate this from -2 to +2, the integral of this, the value of this integral, is going to end up being equal to what I got in part B, which, recall, that was 160.850. So here is an equation that contains a k. I mean, k is contained in the a of x function, but we already defined what a of x is, so this counts. A of x and this thing are equivalent. Here's an equation that we could use to solve for k if we were to do this whole thing out. For this calculator-based free response, we are given this R region here and also an S region. And let's see here. We've got the equation y equals e to the 2x minus x squared. That's this curve here. We've got some horizontal lines through y equals 2 and y equals 1. So based off of all this, we want to find the area of R. Okay, so if I'm finding area between curves, it's essentially going to be integral from left to right of top minus bottom, at least the way these functions are defined. Y equals something in terms of x. So let me start by finding my limits of integration. Even before I do that, I'm going to get tired real quick of writing out this whole equation here, this whole function. So I'm going to define this e to the 2x minus x squared as just f of x. Now I want to see where f of x, this curve, has a value of 2. I want to see where it intersects this horizontal line up here. So I am going to do that on the calculator. To make my life infinitely easier, I'm going to store my f function, this e function here, as y1 in my y equals. And I'm also going to graph out y equals 2 to see where these things intersect. And it looks like on the graph we're going to be intersecting somewhere between 0 and realistically 2. So there's no need for me to really have a much bigger window than that. Let me go to Window. We'll go from 0 to 2, and it's already 2 there. So let me go Zoom 0 now, Zoom Fit. And let's see where these things cross. So there's f of x, e to the 2x minus x squared. There's y equals 2. Let me do second trace, option 5 for intersect. Move my spider closer to that left side intersection. Press enter 1, 2, 3 times. And those intersect at 0.4461. So I'm going to store that. I'm going to refer to that as point P or value P. And I'm actually also going to store that value on my calculator. Let me just quit out of the graph and press store. I'm going to store that as P as well. So now I don't have to type it over and over again or be worried about accuracy. I can just get it back anytime I want. All right, let me do second trace, option 5, and find that other intersection point now. Let's just move my spider over there, because you have to be close to the place you're trying to find the intersection for, and press enter 1, 2, 3 times. It gives me another x value, 1.5539. I'm going to refer to that hereafter as Q, and just like with P, I'm going to store that on my calculator. So let me press the stow button, alpha Q, enter. All right, so now I can get those both back whenever I need to. The area of R, this is now just going to be the integral from P to Q of, now we have to do top minus bottom. The top function is this f of x function that we named. The bottom function is just the line y equals 2. So we're going to have f of x minus 2 dx. And I'm going to just finish this one off on the calculator. So let me do math 9 for integral. We're doing alpha p to alpha q for my limits of integration. And in here, I stored the f of x function as y1. So I'm going to do alpha trace, pull back y1, and then minus 2. I'm basically doing as little rewriting of things as I possibly can. Don't forget to put an x in the dx there. And press enter to get my answer of, now that's kind of small, 0.514. For this part, I want to find the area of S. So the key on this one is recognizing that it's going to be easier basically to figure out the area of R plus S and then subtract the area of R, which we already found in part A. So to get the area of R plus S, this whole area between f of x and the line y equals 1, let me first get my limits of integration. So I need to find where y equals 1 intersects the f of x function. So I'll set those two equal to each other, and let me go to my grapher now. I'm pretty sure I know what these intersection points are, but let me just make doubly sure on the grapher. So here I am again in my y equals, and I don't need the horizontal line y equals 2 anymore. I'm going to just replace that with y equals 1. And let me go now, let's see, for my window, I'm going from, let me go from this time -1 to 3 to get the whole picture of what they gave me there. Zoom 0, zoom fit. So there again is f of x, and now we have the line y equals 1 cutting through that. And I'm just finding my intersection points. So second trace, intersect, option 5. Let me move over to the left side, and I'm pretty confident that this is 0, but let me just double check. 1, 2, 3, and they give us this weird x value, but this is basically like negative whatever. This is their version of 0. The calculator kind of brute forces the intersection. This is such a small number that it might as well be 0 if you round it off to 3 decimals. And it actually should be 0. That's just the way the calculator does things. And then let me do second trace, option 5 for intersect, and let's find the other intersection point, which I'm pretty sure is 2, but again, it doesn't hurt just to double check. So enter, 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 and that is indeed 2. Okay, so now we're sure. We've got 0 and 2 as our limits of integration. So to make this happen, I'm going to find the integral from 0 to 2 of, and I have to do top minus bottom. Now remember, I'm getting the area of S and R together, all in one shot here for this first integral. So that's going to be f of x minus 1, top minus bottom, dx. But now that's not really what I wanted. I just wanted the area of S. So now I need to turn around and subtract the area of R, which we found that in part A. So I defined P and Q as the two intersection points, and I already said what they were earlier in part A. So I'm just going to subtract the integral now from that P and Q that I defined, and then we had f of x minus 2 dx in there. Or I could just subtract the rounded off version of the answer I got in part A. Either way, comes out to the same thing. So let me do all this on the calculator. So here's my first integral. And one thing I'm going to do, I'm going to be a little bit sneaky here. I'm going to do minus. And since I already found the answer to part A on this calculator, I'm just going to arrow up to some past inputs. And this right here, this was the value I got for the area of R. So I'm just going to press enter and plug that in the way it is. Press enter again, and we get about 1.546. For the last part of this free response, they want us to write but not evaluate an integral expression giving us the volume of the solid generated when R is revolved around the horizontal line y equals 1. So for R, my limits of integration, again, back in part A, I found those intersection points. They were P and Q, whatever crazy decimals those came out to. So I'm going to keep using those. I mean, I defined them. I earned it. So I'm free to use them in future problem parts. Now, I need to also figure out the area formula for that I'm going to be integrating over that interval. So my area formula, since my bounded region is not flush against the axis of revolution, since there's this gap in there, I need to use washers. So that's going to be A of x equals pi times big R squared minus little r squared. For big R squared, the big radius, I've got the distance from the further away part of the bounded region to the axis of revolution. So that's going to be a distance of f of x minus 1 gives me that distance there. So that's what I'm squaring for the first thing, for big R. I still have that pi out there. And now for little r, that's the closer part of the bounded region. That's this line y equals 2. So that's a distance of 2 minus 1 here. And I guess I could just write 1, but they told me not to evaluate this, so I don't really need to simplify that at all. So this whole thing is a of x. Now I'm just going to take the integral of this thing from p to q. So p to q integral of a of x dx. And this is the volume. I don't have to do anything else. I've defined a of x right here. I've defined f of x and p and q back in part A, so I am done.